This class, we're going to pick up a new topic on material and energy balance, right? So, but before that, we need to finish up the last things about the alkalinity and the reaction kinetics. But regarding this material and energy balance, um, so here I'm also listing the reading assignment. So it's going to be chapter 4 of the textbook. So I would say that's going to be the most important chapter throughout this course. Okay, so we're going to introduce quite many concepts on environmental engineering, let's say water treatment or wastewater treatment, air pollution, but all of them needs to use this material and energy balance. And more importantly, it's actually the material balance because we need to know what is the quantity of the mass we put into the system and what comes out, right? So you're treating some of them, getting them collected or getting them removed, and you're also discharging some untreated mass into the environment. So that's why I would say it's a quite important concept, and also combined with the basic chemical concepts we have gone through so far. And later on, you will realize actually how we're going to use these concepts in solving the problems. Okay, so please use your time to read this chapter as well. I think it's going to be very helpful. So let's do a quick recap of our last class. So last class, we spent quite a lot of time talking about the acid-base equilibria, or more importantly, is the pH, right? So the pH is basically, we're applying this parameter P as a calculator, right? So pH is just negative of log 10, the concentration of hydrogen ions, okay? So a pH equal to 2 means the hydrogen ion concentration is 10 to the negative 2 m or mole per liter, okay? So you don't have any coefficients or 2 or something else in front of this value here. So based on the pH, we can also calculate the OH ion concentration, right? So that's going to be 10 to the negative 14 minus 2, okay? It's 10 to the minus 12, yeah. So this is because we know that the K water, or the equilibrium constant for water, is 10 to the negative 14. Okay, so this is what people derived in their experiments. So if we know any of these ion concentrations, then we can solve the other one in this, I would say, this couple of ions. Okay, so we also talked about the gas-liquid equilibria. So more specifically, it's about the Henry's law, right? So we were saying that the if you know the pressure of certain gas over a liquid, then you can also calculate what is the concentration of the gas within the liquid. So we said this is very important for the climate change because the carbon dioxide has a very low Henry's constant. So that's why most of the emitted carbon dioxide are in the gas or are in the atmosphere, and that's causing the global climate change. So we also talked about the buffer system. So the buffer system is a system of ions or a solution that can withstand a large change of pH, right? So instead of changing the pH from 7 all the way to 1, right? When you have these carbonate species, you don't have the excess hydrogen ions, and you can basically the pH change will be smaller when you pour these strong acids or base into the solution. So with these concepts, we also briefly went through the process for calculating the pH of a raindrop, right? It's basically using all of these concepts. So the gas liquid equilibria, the acid base equilibria, right? So we can solve that basically for a raindrop, it's acidic, right? Has a pH of around 5.7. So finally, we introduce the alkalinity. So alkalinity describes how much alkali it contains in the solution, or more specifically, how much acid it can neutralize, right? So if we just finish up this discussion, so the alkalinity is defined as the acid neutralizing capacity, right? So basically, it describes how much hydrogen ions it can react with, okay? So if we assume that the water only contains these carbonate species, let's say the uh, carbonate ion or bicarbonate ion, OH ion, and hydrogen ion, then we can calculate what is the alkalinity, right? Because we know for each number of the bicarbonate ion, it can only react with one number of the hydrogen ion. And then for the carbonate ion, it can react with two number of the hydrogen ion, right? For OH ion, it reacts with one. For existing hydrogen ion in the water, then we need to deduct them because they are going to react with these species. Okay, so that's why we have this equation here. So the alkalinity, or the ALK, is equal to the concentration of the bicarbonate ion, and then the concentration of the carbonate ion multiplied by 2, because it's reacting with two hydrogen ions. Okay, and then plus the OH ion, and then minus the hydrogen ion. Okay, so this is the basically the equation that we use to calculate the alkalinity. But we need to make sure that for these units, they all have to be in molarity. Okay, so basically it should be m or mole per liter. Okay, we cannot directly add their mass concentration inside because we need to basically describes how much hydrogen ions they can react with, right? So we know that each of them have a different molecular weight. So we need to convert them into mole per liter first, okay? So that's why in terms of the units of the alkalinity, people can use mole per liter, okay? Or they also invented a term called the equivalent per liter. So the idea of using equivalent per liter is that although it's describing how much hydrogen ions they can react with, but actually there's no hydrogen ions in the water for us to react with it, okay? So that's why we call it equivalent. So basically to show that this amount of carbonate species is equivalent to how much amount of hydrogen ions in the solution, okay? So for simplicity, we also call it EQ dot per liter. So whenever you see the EQ dot, it just means mole, okay, mole per liter. All right, so the mole per liter is equal to equivalent per liter. And because the ion concentration in the water is normally quite low, so people also will use the unit of millimole per liter. So that's just 1,000th of a mole. So that's equal to, basically 1 mole per liter is equal to 1,000 millimole per liter. And also for equivalent, people also came with this unit here, MEQ, milli equivalent per liter. Okay, so it's equal to 1,000 milli equivalent per liter. So based on this definition, if I ask the question, what is the alkalinity of pure water? Okay, with this equation, that water doesn't have any other ions other than hydrogen and OH ion. Okay, so what's going to be the pH if I raise this quiz here? So think about the difference in the definition between pH and alkalinity, okay? So I saw some of you were choosing the pH. So alkalinity is different from pH. All right, 10 more seconds. Okay, we'll stop here. I'll share the results. So most of you are correct, but when I see the number pop up, I think at first many of you chose the 7. So 7 is the pH, okay? So it's just the concentration of the hydrogen and OH ions in the pure water is the 10 to the negative 7, okay? So that's why pH is equal to 7, because you just take the negative log of 10 of the hydrogen ion concentration, okay? So if you plug this in, that's going to be 7. all right? But this is pH. So here we're talking about alkalinity. So when you calculate the alkalinity, you plug in this equation. So it depends on the concentration of the bicarbonate ion, carbonate ion, OH ion, and hydrogen ion. So we said this is pure water, right? Pure water doesn't have any carbonate species. So it's just hydrogen and OH ion. And we know that for pure water, the concentration is the same, right? So basically, it's just 10 to the negative 7 minus 10 to the negative 7, and you will get 0 here. Okay. Let me know if you have any questions about the concept for the alkalinity or pH. We really want to make it clear so that later on, when we see water treatment or when we design water treatment or wastewater treatment system, we need to use these different concepts. Okay. So I would say this is a quite simple example solving the alkalinity. This is directly equal to 0. So what about a real water sample, which we need to really calculate the alkalinity? Okay, so let's spend several minutes so that you guys can spend some time on this question. Okay, so let's say we have a solution that contains this amount of the carbonate ion. Okay, note that here we're using um, the mass concentration. Okay, so this amount of bicarbonate ion, and we know the pH. So what is the alkalinity according to our definition, right? So you can do a quick calculation, or um, at least show the equation to do this calculation. Okay, I'll give you maybe 2 minutes to look at this question. Okay, I think time is up. So let's try to solve this question here, okay? So since it's solving for alkalinity, then we need to refer to the equation to calculate this, right? So if I just write it out again, ALK is equal to the concentration of the bicarbonate ion, or basically the molarity of the bicarbonate ion, plus 2 multiplied by the molarity of the carbonate ion, plus the molarity of the OH ion, and then minus the molarity of the hydrogen ion. Okay, so this is the equation we calculate the alkalinity. Okay, and then it's just converting all of these mass concentrations into molarity, right? So basically, we need to convert that one to here, this one to here, and then regarding the concentration of OH and hydrogen ions, then that's dependent on the pH, right? We briefly showed that earlier. So then how do we do that? All right. So for bicarbonate ion, we know that its concentration is this value, but note that here is the mass concentration. So we need to divide it by its molecular weight to get the molarity or to get the molar concentration, right? So that can be done by 75 multiplied by 10 to the negative 3. Okay, so this is milligram. So milligram is 10 to the negative 3 gram, right? So basically, let me one more person here. So basically, we need to use this value and then divide it by the molecular weight. So the molecular weight of the bicarbonate ion is going to be hydrogen's at atomic weight plus 12 of the carbon's atomic weight plus 3 multiplied by 16, right? So that turns out to be 61 gram per mole. Okay, so we'll divide it by 61 if we just label out all the units here. Okay, so gram per mole, and here you have gram per liter. Okay, so this is the molarity of the bicarbonate ion, or the molar concentration of the bicarbonate ion. Okay, and then we need to calculate the same thing for the carbonate ion species, right? So that's going to be 2 multiplied by 100 gram, or 100 multiplied by 10 to the negative 3 gram per liter, and then divided by 100, or not 100, it should be 60 gram per mole. Okay, so the reason for plugging in 60 is that we just add in the molecular weight is equal to 12 plus 3 multiplied by 16. So that turns out to be 60 gram per mole. Okay, so this is the way we convert these mass concentrations into the molar concentrations. And don't forget these two extra terms. So we have the OH ion and the hydrogen ion. So how do we solve that? So we have the pH, right? So the pH equal to 12 means that the hydrogen ion concentration is equal to basically 10 to the negative 10 mole per liter, right? So this is a definition of the pH. So because we know that the hydrogen ion concentration multiplied by the OH ion concentration is always negative 14, right? So we can calculate out that the OH ion concentration is 10 to the negative 4 mole per liter. Okay. So then we can plug in these concentrations. So we're going to plus the OH ion concentration, which is 10 to the negative 4 mole per liter, and then minus 10 to the negative 10 mole per liter. Okay. So further, you see that quite a lot of these terms have this portion of the 10 to the negative 3, right? So we can make use of the millimole, or the basically the millimole per liter, or the milli equivalent per liter, right? So this is the reason why we define this milli term in front of that, right? We mentioned that the ion concentration in water is generally quite low. So we can get rid of these very small terms by just writing it as 75 divided by 61, and this is going to be millimole, or millimole per liter. Or if we further simplify it, it should be millim, right? And then we have 2 multiplied by 100 divided by 60 millim, right? And then plus 10 to the negative 1 minus 10 to the negative 7 milliamp, right? So basically, we did a conversion of the mole per liter into 1,000 times of the millimole per liter. Okay. So then we have these terms set up. And then what we can say is that this -7 term is so small compared to -1. So we can just ignore this term, all right? And then if you use your calculator and then do the calculation here, you will find that the final answer is actually 4 point, let's see, have it here, 4.66 milliamp. Okay. So further, we know that milliamp is just millimole per liter. Let me just write all the units out, which is also equal to 4.66 milli equivalent per liter. Okay, so this is how we solve the alkalinity. Okay, you can basically confirm whether this number is correct, right? Either right now with your calculator or later after class. Just type in the browser, you can see. Basically, this is the final answer about the alkalinity. Okay. So what this also means is that for this solution here, it's going to react with this amount of the, or it has the capacity to react with this amount of hydrogen ions, right? This amount of hydrogen ions. So further, I would say by convention, what people also would do is instead of showing the alkalinity in this unit, okay, so where they want to show it in a unit that is more straightforward for them to understand. So what they will do is to convert this unit of milliequivalent per liter into the mass concentration of calcium carbonate. So you may feel that why do people do this, right? Because this is adding more complexity into the calculation here. But actually, not all of the water treatment or wastewater treatment facility or staff are engineers. Okay, so they want to understand a term that is more straightforward to understand because calcium carbonate, if you show it in calcium carbonate or the concentration of calcium carbonate, they're just the concentration of rocks or limestone, right? So whenever they want to tune the pH or to understand what is the alkalinity of their water, they want to understand it in the amount of limestone, okay? So for this conversion here, what it means is that we want to find out what is the mass concentration of a solution that contains calcium carbonate that has the same alkalinity with the solution that we're trying to look at, okay? So what is the mass concentration of the calcium carbonate that has the same alkalinity, okay? So it turns out that to do this calculation, what you need to do is just multiply this value by 50, okay? So by multiplying this value by 50, you can convert it into, basically the result is 233 milligram per liter as calcium carbonate. Okay, so this is trying to do an analogy. Okay, so for this water sample here, its alkalinity is the same as the water sample that contains 233 milligram per liter of calcium carbonate in the water. Okay, so they too have the same alkalinity. So then you may wonder how we get this, okay? It is quite easy to memorize it. You just multiply by 50 and then you get what you want. But you can actually try to find out why do we have this same alkalinity in here. So the method we can use is, let's imagine that we have a solution that contains 1 m of calcium carbonate. Okay, so 1 m means 1 mole per liter. Okay. So for this solution here, we know that when it reacts with the hydrogen ions, it's going to react with 2m of the hydrogen ion, okay? Because each carbonate ion is going to react with 2 hydrogen ions, okay? So because of that, for this solution, if we want to know its alkalinity, then it's just going to be 2m or 2 equivalent per liter, okay? So similarly, let's convert it into milliamp. So 1 milliamp of the calcium carbonate is going to have the alkalinity of 2 milli equivalent per liter, okay? So what this also means is that if we just rewrite it in this way, okay? So then 1 milli equivalent per liter means 0.5 milliamp of the calcium carbonate, okay? So 0.5 milliamp just means 0.5 millimole, or 0.5 multiplied by 10 to the negative 3 mole per liter, okay? So what is the mass concentration of calcium carbonate if we have this solution? Okay, so we just multiply this by 100 gram per mole, because the molecular weight of calcium carbonate is 100, right? So what you get is basically 0.05 gram per liter, okay? So 0.5 gram per liter is equal to 50 milligram per liter, right? So basically 1 milli equivalent per liter means 50 milligram of calcium carbonate per liter in terms of the alkalinity, okay? So now, basically, by knowing this conversion, we know that 1 milli equivalent is equal to 50. Then for this problem, we have 4.66, right? So we just multiply this 4.66 by 50 milligram per liter, and that is going to be the alkalinity that's shown as calcium carbonate. Okay, so this is where this 50 is coming from, and how do we convert the alkalinity in terms of the calcium carbonate? Okay. So I know that there are quite many conversions when you solve this problem, but let me know if you have any questions. You also have 2 homework problems this time to do some similar practice, okay? So this time, I think in the textbook, what they also refer to this method as the exact alkalinity. Alkalinity, okay? So compared to that, you also have the approximate alkalinity. So what the approximate alkalinity means is uh, the calculation doesn't, so the calculation doesn't consider these terms. Okay, so if the calculation only considers the bicarbonate and carbonate, then that's approximate alkalinity or rough alkalinity. But when you consider the OH and hydrogen ions, then they are exact alkalinity. Okay, so in the homework problem, you're going to solve this exact alkalinity there. All right, so this is about the alkalinity, and I hope that you're getting a little bit more uh, clear on this concept. Okay, so finally is the reaction or the chemical kinetics. So we talked quite a lot about the chemical equilibrium. So this is where all the ions is coming out, right? So we have the bicarbonate ion, carbonate ion, and then they're following the equivalent constant, right? You can calculate the concentration of the ions. But what the chemical equilibrium um, describes is the final state. Okay, so let's say you have a mixture of ions in a bottle, and then after you place it for some time, it's going to reach to its final state. So that's determined by the equilibrium. But we didn't specify how long it takes for it to reach to final state. It can be 1 second, it can be 1 year, it can be thousands of years, or like the entire time of the universe. So our universe is also is always not in the equilibrium, right? Because it's always changing. It's not as its steady or the final state yet. Okay. But how do we determine how fast it reached to the equilibrium? Okay, so that's going to be the chemical kinetics. So basically, this chemical kinetics describes, as I said, describes what is the time is needed to reach to the final state. Okay, so this is very important for I would say the environmental engineering for water treatment or wastewater treatment. That's because if a reaction is happening so slow, let's consider the wastewater treatment, let's say the organic oxidation. We know that in wastewater, there are a lot of organics, right? We need to treat these organics, basically oxidize them into carbon dioxide and water. And water. But how fast is this oxidation? Is it very slow? If it's very slow, then we need to design a very large reactor and then let the water to stay there for sufficient amount of time before we discharge them into the environment, right? But if the reaction is very fast, then we don't need to worry about it. We can just have a smaller reactor, right? And then send in pretty fast or high flow rate because we know that the reaction is going to take place very rapidly, okay? So because of that, we need to know the chemical kinetics, and that is normally shown in the reaction rates. Okay, so based on the reactions, we can categorize them according to their order. Okay, so we can have the zeroth order reaction, first order reaction, or second order reaction. Okay. So the meaning for the order here is mainly to describe how fast the reactants are being consumed. So let's say we have a reaction of A getting converted into B. You can think of it as organic being converted into carbon dioxide. Okay. So we know that the reactant concentration is always decreasing, right? So we can write out a differential term, dC dt or dCA dt. You know that the reactant is being consumed. So this term is always below zero, right? It's always decreasing. So then we can write it out as dCA dt. We put a negative sign, then this is going to be positive, right? And we call this term as the reaction rate or the losing rate of the A species. So what the zeroth order reaction means is that this losing rate is always a constant, okay? So because of that, if we plot out the concentration of Ca as a function of time, then because it's a constant, what you are going to have is a linear decrease of the concentration, right? So if we write out the concentration of the Ca, then it's going to be C or Ca equal to C0 minus Kt. So the concentration is going to decrease linearly, right? So this is the definition of zeroth order, right? And then the first order reaction means that the losing rate or the reaction rate is proportional to the concentration of the A species. And actually, the first order reaction is the most common reaction in the environmental engineering. So we need to know this concept here, okay? So what this means is that the concentration of A is going to decrease proportionally to the concentration of the A species. So what does that mean? I think from the calculus, you know that we can integrate this equation here. So dCA divided by Ca is going to be equal to negative K dt, right? So if we do the integration, we're going to have log Ca is equal to minus Kt plus C, okay? So further, we can solve that Ca is going to be equal to C0 exponential of negative Kt, okay? Right. So for this concentration here, or for this reaction here, if we further plot it out, the concentration as a function of time, then it's just going to decrease exponentially. Okay, so infinitely time later, the concentration of A is going to approach to zero, but it's not zero yet, right? So we have this exponential term here. Okay, so as I said, the first order reaction is the most common reaction in environmental engineering because not because the reactions are happening in this way, but because it can approximate a lot of the common reactions we see. Okay, so for example, the oxidation of the organics, we can approximate it as a first order reaction. All right. So let's say, for example, okay, so we're talking about the oxidation of some organic fertilizer. fertilizer. Okay, so let's say we have the Mississippi River flowing, right? We have a farmland in here. So we were using some fertilizer here. And then the water is being discharged from this farmland. And downstream of the farmland, we have the city of St. Louis. Okay, this is the city of St. Louis. And we know that the city of St. Louis is mainly relying on the Mississippi River for the drinking water, right? So we have some water treatment plant to extract the water coming out of it, right? So within the river, there are a lot of bacteria which can oxidize these organic fertilizers into carbon dioxide and water, right? So definitely we don't want this water treatment plant to be very close to the farmland, because in that case, we're basically humans are going to drink that, right? So under this situation, we need to know how fast this organic fertilizer are being composed, right? So people actually determine the reaction rates. They found that the oxidation follows the first order reaction. And then they can also determine what is a K value. So if we find that the K is equal to 1 per day, okay, so it means that it reacts with a certain speed in terms of this concentration decay, okay? So let's further assume that the concentration of this organic fertilizer is 1 m, okay, or 1 mole per liter, okay? So we know that the concentration of this organic fertilizer is going to follow the reaction, follow the equation of 1 multiplied by the exponential of negative 0.1 multiplied by t. Okay, so this is basically how the concentration of this fertilizer is going to decay with a function of time. Okay, so then we can know after 1 day, let's say after t is equal to, let's say for simplicity, assume after 10 days. Okay, so after 10 days, then the concentration of Ca is going to be just exponential of -1. Okay, so the concentration decreased, right? So then we can put these standard. Let's say in St. Louis, we want the concentration of this organic fertilizer to be below 0.1 m. Okay, so if we want it to be below 0.1 m, then we can plug in this value. Basically, 0.1 is equal to 1 multiplied by the exponential of minus 0.1 t. So we can calculate how long it takes for this fertilizer to decay to 0.1 m. Okay, so at that point, we can start to extract water and send it to the water treatment plant. Okay, so why is this time important? So we can, let's say we found that this time is 20 days. So if we know this time here, then further, if we make some assumption on the velocity of the river water, let's assume it's, let's say 1 kilometer per day. It's flowing at this speed here. That if we know 20 days is the time that we need for the concentration to decay to 0.1, then we know that this water treatment plant should be 20 kilometers downstream of this farm field, right? Downstream of this farmland. So that's why if we know the reaction rates, if we know the order of the reaction, we can design a lot of systems regarding where we should discharge water or where we should extract water for these plants here. Okay. So I hope this example is clear enough for you to understand the importance of the reaction rates. Okay. So similar to the definition of the zeroth order, first order, we can have the definition of second order reaction, which means that in this reaction rate here, I think I'm occupying too much space here. So in this reaction rate here, the reaction rate is proportional to the square of the concentration of the A species. Okay. So zeroth order means it's proportional to the concentration to the zeroth order, which is equal to 1, right? So the first order is proportional to the concentration of the first order, and second order is proportional to the concentration of the second order. So that's how we classify these reactions into different orders. So finally, it's some note about this K value here. So this K is defined as the rate constant, the reaction rate constant. So the reaction rate constant determines what is the sensitivity to temperature. So note here that we didn't discuss anything about temperature, right? So the K here, normally it increases with temperature. So the higher the temperature, you can think of it as the higher the temperature, the faster the reaction, okay? But unfortunately, people cannot measure the reaction rate at any temperature. So what people do is they'll just measure one value, let's say a K value at 25 Celsius. Okay, so all the other temperatures are going to be interpolated from an equation that looks like this. Okay, so here, you can think of it K1 as the K at 25 Celsius, and T1 is 25 Celsius. Okay, so if we have a higher temperature, let's say very hot summer, 40 Celsius, then if you want to determine the K2, then you just plug in the K at 25 Celsius and then plug in the temperature of 40. Okay, so as we mentioned, the higher the temperature, the larger the K, then what we know is that the theta has to be larger than 1, right? Because if the theta is smaller than 1, then the order of T2 minus T1, which is 15, theta to the order of 15, then that's going to be a value smaller than 1. But we know is that the reaction rate constant is going to increase with temperature, right? So that's why theta is always larger than 1. So a common value for this theta is 1.072, okay? So we can directly plug in this value, theta equal to 1.072, and then that to the power of 40 minus 25, and then you can calculate what is the reaction rate constant at 40 Celsius, okay? So this is for a lot of the common reactions, but for biological reactions, which generally happens slower, people will use the value of 1.035, okay? So regarding the exact values, we're going to mention them. We're going to list them in the problems, okay? So that's all for the reaction rate or the reaction kinetics, okay? So now let's do a review of all the chemical principles, all right? So it took us around 3 classes to go over all of these concepts. Okay, so we talked about what are the atomic number, what is the mass number, what is the atomic weight. So we introduced the ionic and covalent bonds. So the reason or the criteria to tell the difference is based on the electronegativity, right? We can calculate the difference. So we mentioned how many types of chemical reactions we normally deal with. We have the precipitation dissolution reaction, the acid-base reaction, and the oxidation reduction reaction, right? So after we introduced these reactions, we went over how to balance the reactions. We have some tricks in there to balance the reaction because the stoichiometry is very important when we design real systems. So we spent, I think, more than one class talking about the chemical equilibrium, right? So the chemical equilibrium can determine how much ions are being dissolved into the water from solids, right? And it can tell whether an acid or a base is strong or weak, right? And it also can determine the gas-liquid equilibrium, can determine how much of the carbon dioxide can get dissolved into the water. So then with all of these concepts, we talk about the buffer. So we solved the pH of the raindrop. And then finally, we discussed the alkalinity, which determines basically the capacity of a solution that can react with the hydrogen ions. So at the end, just now we talk about the reaction kinetics. And as I mentioned, the first order reaction is a very important reaction in the environmental engineering. Okay, so that's all for the basic chemical concepts. So now let's have our second quiz here to just make sure that you understand the questions or you understand the concepts. This is also a very simple question. So if we say a reaction is a first order reaction, what does it mean? So 10 more seconds. All right, we'll stop here. So most of you are correct. So the first order reaction means that the reaction rate is proportional to the concentration. Okay, zeroth order means it's not dependent on the concentration, right? Second order means the power of two, right? So that's the definition. So if you chose the wrong answer, you can go over the contents again and then try to understand this, right? So finally, I think we have been dragging on this basic chemical concepts for too long. So I think we can use the rest of 3 minutes to briefly discuss the mass balance. Okay, so the mass balance basically determines uh, what is the state of a controlled volume. Okay, so you can think of it as going to groceries to buy, let's say, vegetables or fruits. So let's say we go to buy potatoes. Okay, so I always like potatoes. I like using this as an example, also because I use that in my air pollution class as well. Okay, so let's go. Let's say that we get potatoes. All right. So we can bring certain amount of these potatoes into our home, right? We also consume them at home. We eat them. So if you get too many, then you will place it in your fridge, right, or in your basement. Okay. So that means that there's also an accumulation of the potato at your home. So some of them might turn bad, so they will become solid waste. Okay. So this is a very simple example showing how the mass of these potatoes are being conserved. So if we further list out or try to summarize, conceptualize this process, then what we have is the purchased food, which is the total amount that we bring into our home, is going to be equal to the consumption plus the waste, and then plus the stock, which is the accumulation. Okay, so this is how the mass is being conserved in this system, right? So if we rewrite it, okay, so or if we let's say simplify all of these terms, so what that means is the input is going to be equal to the let's say the output plus accumulation plus consumption. Okay, so people also tend to or prefer to write it in this way. So basically, you just rearrange the terms in there, and then to get a different representation of the reaction. I think my iPad is out of connection, but I think we're also at the right time. So that's all for the contents of this class. And feel free to let me know if you have any questions, and I'll see you next Monday. All right.